Yeah, I think now it works. Cool. So welcome to the lecture introducing Haskell. My name is Luka Kurnjek, and I'm from the company IOG. So a bit about our company and myself. We are called Input Output Global. The webpage is iohk.io because in the beginning we were called Input Output Hong Kong. It was established in Hong Kong, but now we are becoming very global, and we are roughly like around 500 people. We are fully remote, and the people come across 57 countries. So we are a blockchain-based company. We develop open source software that's connected to the Cardano environment. Mostly we use Haskell for development and testing, not exclusively, but mostly. We also do a lot of research together with universities. So we have published 159 papers. And some of the areas we deal with is cryptography, distributed systems, programming languages, economics, and many more. And I personally work in the education team. So what we do, we provide free tutorials and classes. Some are online, so everybody can join them, and some are actually on site. Currently, we are actually working on a Haskell bootcamp, and all the materials are also published online, so anybody can participate. So about the Haskell bootcamp, it's worth saying that in 45 minutes, it's hard to really explain Haskell, but nevertheless, I will try my best. If you then are still somehow fired up and want to learn more, you can check the webpage. It's actually here. All these blue lines are links. So I asked the organizer, he can share the presentation with you afterwards. So you have all the links that you need. And on the bootcamp site, it's actually a GitHub page. You first see the things on the left, and if you scroll down, there are the lessons. So now currently we have only 3 published lessons. You can click on this launch binder and the lesson opens up. It's interactively, and you can look at the code and the text and also execute the code and change something. And there are also lectures. So as I said, 3 are only now added, but if you look at the left side, I wrote there branches, and that's only on the main branch. If you switch to the solution branch, you will get the solutions for the homework. But if you switch to the development branch, the dev branch, there are many more lectures. I think currently like 24. So if anybody wants, he can also try to learn with the development branch. He then just has to go to this folder, lessons, where the lessons file, and you cannot interact with them, but you can anyway read them. This is not the only way you can learn Haskell. On haskell.org, there are many tutorials, many links to books. I just pasted here the section for books. That's how I actually started to learn Haskell. The ones that have the $sign are not for free. The other ones are for free. I think many community members recommend the first one, but I personally rather like to learn from a book. So I think I picked the Get Programming with Haskell book for myself. So that's about if you really want to learn Haskell properly. But nevertheless, we will try now in our presentation to explain some things. So a bit about Haskell. It first appeared in the year 1990. That's quite old. Many programming languages that are widely used today appeared after that. It was designed by around 30 people, which is, I think, quite a lot because some languages started off just with 1 person. The most notable compiler is the Glasgow Haskell compiler. That's what more or less all the community uses. I also found on Google that it was the 28th most popular language by Google searches in 2021. And this is, I think, actually not that bad, considering that there are many languages already today. And Simon Peyton Jones is one of the members that actually led and contributed a lot to Haskell. And if you click on this, it's a link to his lecture where you can find more about how Haskell came to existence. So I took the freedom and copied some of his slides to this presentation. And what he said, like on the left side, if you look down, the history of most research languages is just the quick death. One person designs it, and maybe he asks his friend, please, can you test it out? And after a couple of years, they both just give up. Then you can have the slow death, which is kind of a more graceful death, where some users pick up the language, and then after 5 years, it goes down. And you can publish some research papers, and everybody is happy with it. But then you have the very popular languages that reach quite fast the threshold of immortality. So this means that there is so much code written in them that they are just not allowed to die. They are really needed for the environment. And the problem here is often that because it became so popular so fast, it's very hard to implement important changes, as it happened with Python when they progressed from Python 2 to Python 3. They made it backwards incompatible, and it was very upsetting for many community members. And then Simon also showed like the committee languages, nobody usually uses them. And actually, Haskell is a committee language because it was developed and designed by a committee of around 30 people. But something strange happened. So it didn't happen like this, but it had a bit different journey. And the Haskell's journey was, it kind of picked up slowly in the beginning, and then it plateaued for quite a long time. And this was very good. So this gave the creators time to really work out all the details and implement important stuff. And then later, like from the year, I don't know, 2007, 2008, it started really to pick up. And that's also when industry got interested into Haskell. So what kind of programming language is Haskell? Haskell is statically typed with type inference. This means statically typed, you have to declare a type. Once you declare a type, you cannot use something else. So if you say char A is a char, then it has to be a character. And you declare the type with this double column. And you see here we declare a character and an integer, but then we declare a string. You have these double quotes for strings. And you don't have to write the type signature above, so you can also write it on the right-hand side. But type inference means that you don't have to even provide a type signature or type. Haskell can also guess the type. So if you now declare a variable together and then you sum the character and string and integer, so you have to transform first the integer to a string with the number show, and the character you transform to a string with these brackets, which are a list. You get the result a number 1, 2, 3. And Haskell can guess the type, so it's a string. So a bit more code. We can also import some functions in Haskell. This is an import statement where you import the function is digit from this module. And then you declare a function only letters, and a type signature for a function looks like this. Type of first parameter, then an arrow, type of second parameter, then an arrow, and type of the result. So it's always like chained like this. And when you input the first two parameters, there are no brackets. So in many programming languages, there are brackets, but Haskell don't use them when you input the parameters. And you can use the where clause. So here you declare some helper function and you say, okay, we use the function is digit. So is this character a digit? And then we use the function not to negate. And when you chain functions, then you always have to use brackets. So another way of writing this, we can write it also in the isDigit2 statement. We can use the $sign. So actually the $sign says evaluate first everything that is on the right side and then calculate it, join it with the one that is on the left side. So if you here execute this function and put two characters, which are not numbers, so only letters, you get returned true. But if you put in two characters where 1 is not actually a character, but it's a string, you get an error. So Haskell is very precise, like it doesn't allow you to make these small mistakes. Many errors are catched during compile time. So these are now the two codes I showed you, and we can look now at some conventions. So functions and variables are always written in lowercase. Types and modules are written in uppercase. You see the string, integer, char, these are all uppercase. Also the module data char is uppercase. Then type annotation, as I said, is with double colon, and it's not mandatory. But what is mandatory is the indentation. So here where you see the function only letters, you need to do the indentation for the where statement and then for the next helper function also. So it's not specified how many spaces, but it's good practice that you choose kind of at least 2 and then make it visually nice so that you align these two as digit functions. Tabs are not allowed. Actually, the compiler gives you an error if you use tabs. So no brackets for function variables. I also mentioned this, and functions are first-class citizens. This means that you can pass them around as usual data, as usual variables. They can actually be input for other functions. So the green lines here are comments. The comments start with 2 dashes, and you can also use block comments where you use these curly brackets. So we said now Haskell is statically typed and uses type interference. Another very important feature of Haskell or properties, it's purely functional. It's a pure functional language. And what does this mean? So there are other functional languages that are commonly used today. And this means they are preferably using pure functions and minimizing side effects and mutable data. So what are these properties? Mutable data means variables and functions can change. So it means they can get reassigned values. Side effects means that data comes from some input, user input, web, from randomness, and that's what makes your code unpredictable. And also side effects are real-world effects like printing something to the terminal or some API calls. And pure functions are then functions that only depend, where the output only depends on the input. So no side effects are allowed, no usage of global mutable variables, and no impure function calls. This means you can't call an impure function inside a pure function. And functional style is aiming towards these goals. Now, purely functional style, this means you can still allow impure functions, but they always have to have a type signature that indicates side effects. So you always know which code you are dealing with, whether it's pure or impure code, and all variables and functions, pure or impure, are immutable by default. So this means in Haskell, once you declare a function or a variable, you can never change it again. So it means if A is 1, you can never say A will be 2. And this has some practical implications. So pure functions take at least 1 argument or more. If they don't take an argument and calculate something, it's not a function, it's a variable. They always return a value, so it never can happen that they wouldn't return a value since they would be useless. They cannot make any print statements if they are pure, and they are predictable, and that's very good for debugging. So here we have a function that takes a string and returns a string, and it just checks. If the string is in this format of an IP, a local host, it says it's a local host. If not, it says it's not a local host. And this if then else statement always has to have this structure because it has to return a value. You can never write if then without the else. So that's important. And what most programmers are probably worried about, how will I program if I cannot use any for loops? Because in for loops, you have index, for instance, that loops. So say your index goes from 1 to 10, and it changes in value, and this is not allowed in Haskell because this would be a mutable value. So an alternative in Haskell are many helper functions that work on lists. And before we go to those helper functions, let's shortly look at what are lists. So they are data structures where all elements have the same type. Here on the right side, you see you have a list of 1, 2, 3, 4. And actually, you construct a list. You could construct a list with the const operator, which is this column. You say 1, const 2, const 3, const 4, and you always end with an empty list. And the string is basically just a list of characters. Okay. So what are the helper functions that work on lists? We have the map function. The map function just takes a function in a list and maps the function on every element of the list. So the type signature here above, it doesn't use any integers or doubles. It uses normal letters, and this means this is a type parameter. It means it can be any kind of type, but once you pick an integer for A, then also this second parameter has to be a list of integers. And same if the function returns a double, then the returned parameter should be a list of doubles. And how this works, here we have a function at n to list. So it takes an integer and a list of integers, and it just maps the function plus n. So for the number 2 and the list 1 to 3, it returns 3, 4, 5. And the filter function works very much the same, just it kind of filters out the values that don't pass a condition. So actually, let me just put this video down. Okay. So actually, if you say larger than 5, then you filter out all the values that are below 5 or 5. So for 1 to 8, you get returns 6, 7, 8. And you have the fold left and fold right functions. These functions kind of fold together a list. So if you provide a function that's called like subtraction, and you start with 5, and you have 1 to 4, you say, okay, 5 minus 1 is 4. Then you take 4 and you say 4 minus 2. And like you iterate from left to right. So if you look at the middle column, it goes 1, 2, 3, 4. And you end up with minus 5. But you can also fold it from the right side. And here you start actually with the elements of the list, and you start from the right side. So the first column goes 4, 3, 2, 1. And the end result is very much different. And these functions help you in Haskell to program things that are usually done with for loops in conventional programming languages. But that's not the only way. You can also use recursion as an alternative to for loops. This means functions calling themselves. And here you have a function myProduct, which should take a list of integers and then just multiply all the elements and return an integer. And we use two helper functions called head and tail. So if you look below, head gives you the first element of the list, and tail gives you everything except the first element of the list. And we see here in the myProduct tick function, then we have the where statement where we say multiply xx is. We have an if, and then we say else head xs multiply, and we call multiply again. So this is an example of recursion. And experienced programmers usually avoid a bit recursion because for complex functions, this can get a big headache. So following recursion in your mind, it's not that easy. And in Haskell, we help ourselves with pattern matching. So here on the right side below, you can see two implementations of the function head and the function tail. And pattern matching means like you match the values. In these brackets, you say my head in brackets x colon xs. You map the first value to x and the rest of the list to xs. And this is just how you could implement the head function. And For the tail, you just return XS because it's the rest of the list, and you get 2 and 3 returned. And now the function myProduct with the tick, we can rewrite it much more simpler if we use pattern matching. So we say myProduct for empty square brackets. For an empty list, we just return a 0. For a list with one element, we just return the one element. And for a list with many elements, we say, okay, let's take the first element and multiply it, and then recursively call this function again on the tail of the list. And this is a way how you can more easily write recursive functions in Haskell. So Haskell is also lazy. It sounds a bit funny, but what it actually means in Haskell, functions and variables are lazy because they are evaluated only when they are needed. If you have now here on the left side, you look at the multiply function and you just multiply two integers. And then in the main function, you declare, okay, this is variable 1, where I multiply these two values, and variable 2, where I multiply two other values and variables, and in the end, I just print variable 1. Now, because Haskell is lazy, variable 2 never gets computed, and also these values in the brackets, 1 multiplied by 1 and 1 multiplied by 3, they never get evaluated. And actually, in Haskell, you have the option to strictly evaluate everything, and you can add a language pragma. So a language pragma is something that adds some features to the Haskell programming language, and we use here the bank patterns. And this means that you can put this exclamation mark before a variable like var1 and var2, and that they are then strictly evaluated. And now we can talk about what this really means if something is not evaluated. So Haskell still has to keep track of what would be needed to evaluate it, and it builds up so-called chunks. These are promises. And the benefit is that code that is not needed is not computed, so you save resources. But the downside is chunks cost space allocation. And also afterwards, you have to clean the chunks. So for this example, we actually had to, Haskell had to create 10 chunks. So 1 plus comes from the chunk for itself to be identified as a chunk, and then plus 3 is for the two parameters and the add function, and plus 2 is just for the 2 parameters inside because the multiply function is already known to Haskell. And actually this code, which does almost the same as the other one, is much more resource friendly. So if you use strict evaluation, it's better in this case than if you wouldn't use it. And our company actually uses only strict evaluation, but in some cases also laziness can be a benefit. Okay, so we talked now about what kind of programming language is Haskell. We said it's statically typed with type interference, it is purely functional, and it is lazy. And now I want to talk a bit about the practical benefits of Haskell. So let me drink something. Haskell has much less runtime bugs. Runtime bugs are those bugs that happen once you run the program. So after you compile it, you give it to some users, and then they run it. And this is because the compiler catches a lot of compile time errors. So null pointers are not possible. What are the legal values of a parameter are usually trivially answered. Wrong argument order is likely to cause type errors, but wrong argument count will definitely cause type errors. And I took this from a Reddit discussion. So there are many opinions that clash. And if you are curious, you can also view this discussion and look at what people think about. So Haskell has also some data types that handle errors and missing values. So a data type is declared with the keyword data, and then you say the name of the type, like data bool, and it's either true or false. So in this case, you don't need to write this because bool is already an internal data type of Haskell. But I just wrote it out that you see how it looks like. And there are two data types that are also internal in Haskell, and they are called maybe and either. And the maybe data type, it's a parameters data type, which means there is a parameter a to it, and it has the values nothing or just a. So in practice, this means the following. If we have like this function myInit, we can say, okay, let's take the initial value of a list, but if the list is empty, we return a nothing. And if the list is not empty, we return just the first element. And in practice, this means if you just call it on a list of integers and say this is a maybe integer, you will get return just one. But if you call it an empty list, you will just get return nothing. And this is good to handling missing values, but sometimes you also want to include a message, like what is happening if a value is missing. And then you can use the either type, and you have a left A and right B. And for the practical example of the init function, you could say, okay, let's parameterize it by a string. And if it's an empty list, we say left, this is an error, the input list is empty. And right, if it's actually not an empty list, we return the first element of the list. And this is very helpful. So this can help you to catch a lot of bugs. There is a question down, can you spot the compile error in myInit? Tick. And the compile error is here in the first line. So in the type signature, we say myInit : take a list, type A, and then return either a string or a list of type A. And what we actually return is just either a string or an integer, so not a list. And this is a good example. If you make such a small bug, Haskell will definitely complain when you compile it, and you can then easily correct it. So in Haskell, there are no bugs also because of mutable. I should write here mutable data. This is a typo. So in many other languages, you have mutable data. As for instance, in JavaScript, I put some code here. And if you have like a function where you just add some numbers to the items, so here below you see we create an empty list with 3 items, and then we call this function. And for every item, it should return a function where you say, okay, for the first one, we return 0, for the second one, we return 1, and for the last one, 2, and so on, if you have a number of 3 items. But what actually happens if we look at this data, we see all of them return 2. And the problem here is we use this var keyword, which has global scope, and the data is mutable. And the I exists outside of the for loop, and it gets its final value at the end of for loop. So all of these 3 get assigned the function where it should return 2. And this is now a very simple example, but these bugs in real life actually do happen quite a lot. And there has to be many testing also to catch them. But in Haskell, such bugs are not present. So another nice feature is also state control. Here in this code, in the beginning, we declare a type, and we use this record syntax. I will explain a bit later what this is, but record syntax just means that you kind of declare a type where you can nest some other types inside it. So we say, okay, let's create a player, and the player has some lives and attack, and they're both integer. And we say deriving show just so we can print this data in the end. So we say player 1 then has 15 lives and 10 attack, and player 2 30 lives and 5 attack. And then we write a function score where we actually take two players, an attacker and defender. And if the attacker has still some lives left, then he can attack, and the defender, the lives of the defender get subtracted. And because in Haskell you cannot have mutable data, you always have to create a new variable if you want to kind of simulate a fight. So you say, okay, let's score player 2, player 1, and then we create player 1 first round. And then next we score player 1 first round against player 2, and so on. And in the end, we come to the third round. So this looks like a bit of a hassle, but it has an important advantage. So here are the results. You see that the player 1 third round got 0 lives, and player 2 third round got still 10 lives. Now, if you want to switch those 6 statements in any order you like, in most of the programming languages, you will get an error because the compilers, they treat one line at a time. But in Haskell, because everything is predetermined, if you use only pure functions, it doesn't matter. You can switch those lines as you want, and this is very useful. So when you use concurrent programming, for instance, where you have programs that run on multiple cores parallel in the processor, some really obscure bugs can happen. And if you use Haskell, it's much more easier because you have full control of the state. And this is very good when you do much high-speed programming. I think Haskell is often also used by banks. And one reason could be that they just want to be very secure in their code, because people could lose a lot of money if there is some bug. And the other one could be also if they have developed programs for high-speed trading, so which definitely run in parallel concurrent programming. So this is another feature. So another benefit, it's not really a benefit, but I want to talk a bit about speed, because Haskell offers so many interesting things. You could maybe say, okay, but how fast does it really run? And the truth is, it doesn't run as fast as C++. C++ is one of the fastest languages. And I wanted to do a comparison. So I wrote the quicksort algorithm that just takes a list of integers and sorts it with the quickest possible way. And I found some code for C++ for the quicksort algorithm, which is quite popular and well known on the internet, and compare the time for compiling the Haskell program and the C++ program. And you see, so Haskell used up 849 milliseconds and C++ 334 milliseconds. And it looks like quite a lot, but you have to understand C++ is one of the fastest languages. So if you compare other languages, Java or I don't know, C#, Haskell is still somewhere there where he can compete with all the other ones. And here in the second row, you see I used run Haskell. So Haskell can actually be also used as an interpreted language. So it means here you don't compile anything, you just interpret the file, and this is then faster than if you compile with C++. Of course, if you do this with Python, Python will be much faster than Haskell, but still it's a nice feature that you have a language where you can compile, but also interpret things, and this is not very often found. And by the way, if you check this code here on the link, you will see it's like 30 rows of code, and here in Haskell, it's, I don't know how many, maybe a bit more than 10. So Haskell is also much shorter than other languages. And that's also our next point. So Haskell is elegant and has many features. And for comparison, I took some Python code. So here we have a function that takes in a number and computes all the prime numbers up to this number. And in Python, you have like around, I think, 8 lines to do this. And here is the Haskell code. And there are 5 lines, but you have to know you can scratch the first one. So the type signature is not obligatory. And you get to 4 lines. And you could even put the last line above, so it would be 3 lines. But let's say that you can also compress a bit the Python code to 6, from 8 to 6 lines. So you can still see like Haskell code is around 50% shorter. It's of course not generally always like this, but it has a reputation that you can write things very compact. And what actually this function does, so here you take in the number and you construct a list from 2 to n, and then you call the helper function filter prime. And if filter prime gets an empty list, it just returns the empty list. But if it gets a non-empty list, it says, okay, take the first element, which is 2, it's a prime number, and then again call filter prime numbers on the rest of the list. But the rest of the list is then modified in such a way that all the numbers divisible by 2 are filtered out, and then you repeat this. And the first number again gets added, which is 3, and then all the other numbers divisible by 3 are filtered out, and so on. And with Haskell, the code is shorter, but you also have to think a bit more, because in Python, if you follow this, it's maybe a bit easier because there is not really no recursion here. There are just for loops. But in Haskell, you have to first think, okay, well, what does this recursion really do? And this is also good training for your mind. So you definitely become a good programmer also if you, in other programming languages, if you start to code in Haskell. And some other features of Haskell are partial application. So partial application means if you have like a function multiply, where you just multiply 2 values, you can just call it with 1 parameter instead of 2, and you get a new function. And this new function now just takes in 1 parameter and it multiplies it with 5. So if you print this here out, it's the same as if I would first call mult with only 5 and put brackets around, which would create a new function and then input the number 2. But there can be some bugs if you are not careful. So let's first explain what's a lambda function. A lambda function is an anonymous function that you create on the way, and you just say, okay, backslash, here are my 3 parameters, and then an arrow, and this is the function body. And this is now very similar to the left side function. We just added 1 more parameter. And now here down in the main function, you can see, okay, we declare 2 variables, var1, var2. And then we create mult with 5, where we use the mult function and input 1 variable. And we try to print then this function with another variable, but we get an error because the final count is just 2 variables. So we are 1 variable short. And this is a bug that can happen if you use a partial application. But programmers learn this from very early on. So it's not really such a big issue. And partial application can still be very useful in practice. I also talked already about pattern matching. So one way that you can use it is you declare a function where you just match some values and you say, if I get these values, I get some strings return. So if you are 1 year old, it's your first birthday. If you're 18, you're an adult. If you're 64, in a fair country, you can retire. But for any other age, it's nothing special. You only have to be aware if you switch this order and say, okay, for any age, I get nothing special. This function will always return nothing special, even if you input 1, 18, or 64, because it matches always the first case. So the general case should always come at last. Okay. Another feature of Haskell are also sum types and parameters types. We have seen them before. So if we create a data type, bool is an actual Haskell data type, but just to write it out, it has either the value true or false. And this is a sum type because it's combined with the logical OR. We could also create another data type called fruit, and we say apple, kiwi, mango. And then we have parameterized. I think this is actually a typo. Types as maybe and either, which take in 2 parameters. Either takes 2, maybe takes 1. And you can also write your own data types that have a parameter. So if we say fruit A, we can say apple A, kiwi A, mango A, and fruit prices could be a list of fruits with a parameter integer. And then we just say we have an apple 2 and kiwi 3, and those numbers could be representing the prices in dollars. And so these are sum types, but you have then also product types that are combined with logical AND. And a fruit pair is then actually a sum type where you have like a pair of 2 fruits. And this is what is usually used in imperative program languages, so the languages that are not purely functional and or functional at all. And it's very difficult to refactor code. So if you have a big store that has some code that handles all the items, when they decide we want to add some new items, the programmer has a very hard time to refactor the code when he has to deal only with product types. And often usual languages only have product types. But Haskell has also sometimes some types, and it's much easier to refactor the code. So we have record syntax. We have seen it in the player examples before. You can define also a data type where you kind of nest in other types, like some book data. And then there is here a store item where you can combine already those existing custom types. So before we had fruit, and we say, okay, food is of type fruit int, and book is of type book data. And if you then declare any variables, you say food is the type constructor. So you write it first, and then you say apple1, or you say book, which is also the type constructor, and then you say book data. And when it is published, prior to, and for record syntax, you always use those curly brackets. Or you could also say book empty and no data available, because I defined it here. Okay, this is record syntax. A very important feature in Haskell are type classes. So GHC is actually the interpreter for Haskell, like in Python. And if you use the command :E for a type, you get a list of all the type classes this type belongs to. And then you can use the :E command on those type classes, and every type class defines a set of functions. So for instance, the num type class defines the function plus, minus, multiply, and so on. The show type class defines the function show and others. And the bounded type class defines not really functions, but only variables. And this means if I have a variable that is of type int, I can use all the functions that this type gets because it belongs to these type classes. So I can use the plus function, I can use the show function, which transforms an integer to a string, or I can say, okay, for an integer, give me the maximal bound, and this is the largest number an integer can have. Haskell also has another type called integer. So we have int and integer actually doesn't have a maximal bound, so it can be unlimited. You can also implement a type class on your own. So if we here have an add function and we just add 2 values, we don't have to say this is an integer. It takes in 2 integers and returns an integer. We can just use a parameters types, and then we say this type has an instance of the type class num, And if we declare our own type like number and we say 0, 1, 2, and we derive show so we can print it and enum that is enumerated, it means that we have now a type that we can implement our own class num. So if you derive something, then it's implemented automatically. But for num, you cannot do this because Haskell doesn't know how to exactly do this for this kind of type. And we say here, okay, we use the from enum function, which for this type returns a number. It means like 0 gets assigned 0, 1 gets assigned 1, 2 gets assigned 2. But if there would be any other names like 1, 2, 3, the numbers would be still the same, 0, 1, 2. And if we do some calculation here, we can say, okay, this is now what happens if we use the plus function on these two parameters. So then you can actually use the add function for this custom type. So you see here we use add var1, var2, and it's like 1 plus 2, and it gets returned. It should be just a moment. Yeah, this is also, okay, I said 1 plus 1, yeah, it returns 2. And 1 plus 2, it returns 0, because I defined this plus function in such a way, it never goes above 2. So if it gets 3, if it would get 3, then it starts again with 0, and so on. And this is a way how you can like define your own types and then say how functions should work on them. So plus is just one function of the num type class, and you could also define other functions how they would work on them. The most prominent type class is the monad type class in Haskell. It has 3 functions called bind, sequencing function, and return. So what does return do? It just puts something in a context. So if you have a string and say this should be a maybe string and use return, then you get the just Haskell. The sequencing function allows you to chain together some actions. So if you, for instance, say print learning and then print Haskell, you can combine these two with the sequencing function. And here is a bind example. So you have like a parameter a, which is maybe int, so it's just 1. You have a function that takes in an int and returns a maybe int, so like x plus 1, and then it says just this number. And now how you want to use, how can you use the function with a? Because a is of type maybe int, not int. So this would not work if you would just say func space a. But you can use this bind parameter, which takes the int out of the maybe context and then just applies it to the function. And you get return just 2. Now, this doesn't look very impressive, since I said that monad is the most important type class. But what it actually allows you to is to write very, very nice code. If you remember, I said you can use the sequencing operator to chain something together. And the truth is, in Haskell, you cannot write like here on the right side, just some statements, because everything in Haskell needs to be a function, and also functions need to be chained together into one line. But the reason why we can still write those lines separately is because we use this do keyword. And the do keyword, what it actually does, it translates all these lines to this code on the right side, where you actually use this sequencing operator to chain it together. Then you use the bind operator to get some data out of the context. You use some lambda function, and you use the return function to put everything back into the context. And this is now actually valid Haskell code, because everything is just like chained functions, one with each other. But to make your life much easier, you can just use the do notation and then write it in a much more nicer way, and Haskell will translate this for you. So this is one reason why the monad is so famous, and the other reason is also, of course, input output is a monad. has an instance of monad, and all, as I said in the beginning, all impure functions need to have a type signature, and this is the type signature. So if you say input output, then you are allowed to have side effects. You can print something, you can read something from the command line, you can make some API calls, and then you know this is impure code. And you can always strictly separate your pure code from impure code. Another feature of Haskell is property testing. So Haskell was the language where property testing was invented. It was invented by the developers of the Quick Check library. And this means in many programming languages, you basically just hard code your test. You say, okay, I have some functions and I will make up some data, input data, and then I expect the output data should be like that. But in Haskell, you can actually define properties, and you say, like, let's have a property preserve length. It takes a list and it checks whether the length of the list is the same as the length of the list when you apply the quicksort function. So we defined the quicksort previously. It's just a function that sorts a list. And we want to check whether when you apply this function, the length of the list is preserved. So no data gets lost or no data gets added. You can also have a means, okay, if I apply this quicksort, it should sort the list. So if I apply it 2 times, it shouldn't be changed. Or you can use the built-in function Haskell sort. So you say quicksort should actually work same as sort. And these are now properties. And what the Quick Check library does, it generates the input data. So instead of you having to hard code the input data, Quick Check will generate the data for you, and you can say how many. So it can be 500, 800,000, as much as you want. And in the end, it tells you whether, okay, it's fast, or it tells you, no, it failed. And it tells you after how many tests and shrinks. Shrinks just means that it simplifies the input data, and in the end, you get a simple example that failed. So this is very, very useful in Haskell, that you can run many tests for your code. So these are more or less all the features of Haskell. Haskell has also a very friendly environment, user environment. So it uses Hoggle and Hackage. Hoggle is kind of an API search engine, which allows you to search libraries from Haskell. You can write in a type signature or a name. And once you get, like, for a function, the link, it redirects you to Hackage, which is the central repository. It contains many packages, I think, yeah, 15,000, around 15,000 now. And it has a lot of descriptions. So for every function in a package, you have a description, you have sometimes an example, and it's much easier to learn some new code if you are looking for something specific. In the end, I just want to mention the software that we develop. Among them are Plutus. So this is our native smart contract language of Cardano. We use also Marlow, which is a domain-specific language built on top of Plutus. And it's just for executing financial smart contracts. It has some limitations. So it cannot do everything Plutus can do, but it's much more easier to write. And we have also Atala Prism, which is kind of an identity platform for verifiable data and digital entity. These are not all of our products. We have much more. These are the ones that are most well known. And this is how, for instance, looks some Plutus smart contract. It's actually Haskell code. So Plutus, when you write Plutus, you write Haskell code. You just use some specific functions and libraries that we develop. And this function, what basically does, it checks if a transaction is valid, and it says it's only valid if a certain person signed it. So every person has some private and public key, and it checks, okay, this is the right person, and also if the deadline is reached. So the person can only reclaim the money after a certain deadline. And it maybe looks complicated, but actually these are just some long names, else it's very simple Haskell code. So you have 1, 2, 3 input parameters, and you return a bool. And if the bool is true, then the transaction passes. If it's false, it fails. And in the end, I would just say why we use Haskell. So our aim is to provide access to access for financial services for 3 billion people that have none. So in the world, more than 3 billion people actually have no access to banks. And they first need a digital identity. So we work also on that. And then we use blockchain technology and smart contracts that would enable them some funding like microcredits or something like this. And our CEO, Charles Hoskinson, he often is saying, if you're building something for everyone and you're building it to last, build it well. So we try not to rush, and we try to really test our code and think it through. And Haskell can give you a lot of assurance in your code. So bugs are still possible, but there are much fewer. The first smart contract language was Solidity, which was developed by Ethereum. And in the Ethereum ecosystem, in the beginning, there was a very big crowdfunding project called the DAO that raised $150 million. And because of some bugs in the contract, around $50 million was drained, which was quite upsetting to many people. And the project got canceled, and then an Ethereum hard fork happened that produced another version of Ethereum called Ethereum Classic. So you can see that bugs have very important implications, not just about people that can lose some money, but also on the ecosystem where some people can just split and say, we want to go in this direction, and others say we want to go in that direction. So in the end, nobody lost the money because the hard fork reverted this, but still people notice that writing smart contracts is not that easy. You have to check them very precisely, because once you submit them, they cannot be changed. Once they live on the blockchain, this is code that lives there forever. So when you get the slides, if you will be curious, we have a lot of education that we provide. Here you have some links. We have pioneer programs where you can learn some of our tools that I described. We have playgrounds where you can test these smart contract languages online. Then we have YouTube channels where there are many interesting lectures, and there are also books about Cardano. Two you have to pay for. The Plutus Learning a Smart Contract Language is for free. It's based on the third cohort of the Plutus Pioneer program. But now there will be a fourth cohort, and we will make many updates. So it's also worth checking what are the newest resources. There are also many interesting Cardano projects. So Cardano stake pools are sometimes joined in this climate neutral Cardano project, where they use only renewable energy, and they also finance other environmental friendly projects with the money that they make. One of this is called Cardano Cafe. If you are interested, you can Google it a bit. And this is more or less it. We are not the only company that is using Haskell. There are many others. You can see also Facebook is using a bit of Haskell, and GitHub, which is very well known. Some of the companies here below also work for us because we are such a high, how would you say, we produce a lot of Haskell code, and then of course we sometimes don't have enough people and hire also other companies. And here you have also a GitHub list where you can check many other companies. I think there are currently 175 on the list, but definitely not all of the companies that use Haskell are there. That's it. What do people say about Haskell? My colleague said when learning Haskell, it was as learning to walk again. Some people from successful companies say that when you program in Haskell, you are like on an autopilot, because it really directs you in the right direction, how you should design your code, and runtime bugs are much less common than in usual imperative languages. I personally think that Haskell is kind of the holy grail of programming languages. When you will get the slide from the organizers, here is a conversation between a bear and a scientist, and they kind of, one tries to explain to another how to build some Haskell code. And if you will be laughing, that's a good sign that you understand Haskell. So that was kind of indicator for me. When I started to laugh about this conversation, I understood, okay, now I'm slowly getting how Haskell really works. And that's basically it. So thank you for your attendance.
Thank you. Thank you so much, Luka, for taking the time to talk with us. I did take a sneak peek at your slides before you began, and I read that conversation, so I can vouch that it is quite funny if you've done your homework. And we've had some pretty great Haskell code come out of this conference, so I'm sure lots of us will find it funny. Thank you for your great talk. I think Haskell and using it to create better smart contract programming languages, is a really cool application for some time. So I'd recommend checking out those educational resources. I've looked at them also, and I can vouch that they're really quite incredible and also quite fun. So I'll share the slides with everyone so they can take a look at those links. But I just wondering if anyone has any questions for Luka. It seems like Bernat has a question.
Yeah. How does using Haskell help scale to more users/developers for Cardano?
To more users and less developers?
Well, no. So to scale to more users and developers.
Scale to more users and developers. So with the developers, it's like how much you need and how much you can afford. So I can say for this section, I mean, there are enough Haskell developers that are willing to apply for companies. I noticed that I think the ratio between demand and how much resources are available in Haskell is not that critical that companies wouldn't find developers. But for users, it's like this. In the end, the user doesn't really care in which programming language it's written, only if it's a user that develops smart contracts. So he has to use Haskell. And we noticed that this is a quite big hurdle for people. So many programmers don't want to start with Cardano because Haskell is such a different programming languages, and they need to kind of take some time in the beginning, sacrifice the time and learn it. That's why we also decided we will now make this bootcamp and start to also teach Haskell. So it's definitely not that easy as if you would use JavaScript, which is one of the most common languages.
Sorry, wouldn't it be possible to, like in Ethereum, you have different languages that all compile to the virtual machine, to code that the Ethereum virtual machine can run? So Cardano has a similar structure, or it's very different from Ethereum?
So I don't know how much similar is the underlying structure, but we are definitely aiming at this. So for Marlowe, you can already now write code in JavaScript. So this is already possible. And I think for Plutus, they are now also enabling TypeScript. So TypeScript is actually JavaScript. It only has some additional rules where you also have type signatures and such stuff. So we are really thinking about this. I think in the future, this will also happen. But we started out with Haskell because even though people don't catch up so fast, it has still much other benefits that make the code more secure.
Yeah, I agree. Thank you.
You're welcome.
I think there is one more question in the chat, which is, what are some practical examples of like using function application, like partial function application, sorry. What are some practical use cases where you'd want to use that?
So for now, if the person is asking just functional for functional programming, You can use it like when you want to have code that is more safe. So previously I worked in a company that was one of the leading companies in the world for developing control systems for particle accelerators. And we did this mostly for the medical sector. So when you have a cancer patient that gets irradiated with an accelerator, there's some gamma rays and the cancer will try to destroy the cancer. We developed all the software like how to control this process. And if you have a bug there, this is very dangerous. So when people's lives are at risk, you want to be very sure of your code. And they actually used part of the code was programmed in Scala. Scala is also a functional language, but it's not purely functional. So Haskell, in this sense, is a bit more safe. That was just the decision of the company. They said we will rather use Scala. In this company that I work now for IOG, we are building kind of financial systems, you know, and if you have a bug and people can use $1 billion in some strange circumstances, this is also very critical. So for finance and for maybe other sectors where there is a lot of stake at risk, you would use functional programming. Banks also use it, yeah.
And I actually have one question too. I was wondering, since you did like a whirlwind tour of all these features of Haskell, what feature of Haskell is personally your favorite and you find yourself like enjoying the most when you program Haskell?
I would say the best feature of Haskell is because you can't have mutable data, so you can't reassign data. It's more predictable how you can write code. So you have much more possibilities in other programming languages, but having a lot of possibilities is not always good. So you can still write all the code in Haskell that you write in other languages, but Haskell directs you more in a way, you know, you sometimes don't need to even write code. You need to figure out, like if you need 5 functions, you figure out the type signatures. And once you do this, then you already have kind of set your path, and it's much easier to kind of follow just this path and implement it. And in other programming languages, because you have so many possibilities, bugs are much more common. And I think programmers spend sometimes more time with debugging than just coding. And in Haskell, I think it's not always this case.
Yeah, thank you. If there are any other questions, does anyone have a final question? Okay, it looks like no, I don't see anything in the chat. So I just want to thank you again, Luka, for giving us your time. That was a really interesting talk, and I think it's really helpful to reestablish the Haskell foundations, but also give us some stuff to look forward to. And like I said, I'll share those slides with everyone, so hopefully everyone can take a look at those educational resources. But just thank you for taking some time out of your Sunday to talk to us. It was a lot of fun.
Cool, you're welcome. Thank you for inviting me.